Hi students, in this lecture I am going to discuss force acting on a current carrying conductive wire. Let us see force acting on a current carrying conducting wire. Let us take a straight wire. So this straight wire carrying current I, its length equal to L. It is placed in a uniform magnetic field. It is B bar. Then force acting on this is given by, so magnetic force acting on this, it is given by I into L bar cross B bar. So this is based on observations I into L bar cross B bar. And in this direction of L bar, it is direction of current. And direction is given by, it is a cross product L bar cross B bar. And we know how to find direction of cross product. Okay. So this is what we are getting based on the observations. This is for straight wire. Now, if it is not a straight wire, then how to find force acting on that wire? Let us take wire is now like this. This is a current carrying conducting wire. It is not a straight one. And in that current is now I. So current is I. See how to calculate. We are taking now small element in that conducting wire. Small element. Its length is now dl. Then force acting on that. It is given by df bar. That is equal to I into dl bar cross b bar. This is a magnetic force acting on that small part. Like this, we have to consider all small elements starting from here. Let us say this is point A and this end is B. From A to B, we have to consider all elements. Okay. So total force is given by F bar equal to integration of I into dl bar cross B bar. Now, since we are taking uniform field, if it is uniform field, we can take B bar out of integration. I is a constant taken outside. Integration of dl bar cross B bar. So we are taking B bar outside. Condition is it is uniform field. If field is not uniform, then we cannot take it out of the integration. Okay. Now we have to focus what is the value of integration of dl bar. Now see carefully. dl bar is one vector. Direction is direction of current. So taking like this dl bar, next dl bar, like taking small elements, okay? It is now combination of n vectors. And resultant of n vectors, we have learned in vectors, polygon law of vectors, right? Then resultant of all these vectors is given by the closing side taken in reverse order. That means it is now from A to B, imagine one vector. From A to B, imagine one vector. That becomes now L bar. So according to polygon law of vectors, it says resultant of these n vectors is given by the closing side taken in reverse order. That means connecting tail of the first vector and head of the last vector. This is now L bar. That means whenever conducting wire, if it is not a straight one, what we have to do? It is simply finding what is the position vector of the starting point and position vector of the ending point. I can take it like this. L bar is equal to position vector of B minus position vector of A. This is giving us L bar. Okay. Like this, we can find a force acting on a wire which is not a straight one. Now let us consider it is a conducting wire which is a carrying current. It is a closed one. It is now closed one. So when it is closed, see what is the value of, means if you observe separation between end points. When it is a closed one means loop, there are no end points, right? That means modulus of L becomes zero. That means force acting on a current carrying loop is zero. So this value becomes zero for a loop. See here, this is not a closed one. So we are taking the closing side taken in reverse order. So this has some length, right? But when it is a closed one, there is nothing to close. That means integration of dl bar gives zero. So condition is on a current carrying conducting loop, current carrying conducting loop, magnetic force is zero. Condition is that field is uniform. V bar is uniform. If it is not uniform, we cannot take V bar outside. Okay. So force on a current carrying conducting loop is zero if field is uniform. Okay. Right. Now see carefully. So when we are taking a conducting loop, loop means closed one. It can be any shape, need not be circular. So I'm taking a circular, but it can be any shape. Loop in the sense closed one. Let us take now a closed one. Suppose current is now I, which is now anti-clockwise. So for us, this is anti-clockwise. And if you see behind this screen, it will be clockwise. Okay. So now what I'm saying here, a current carrying loop is acting as a magnet. I'm repeating, a current carrying loop is acting as a magnet. And when we are saying a magnet, it has north pole and south pole. Okay. And you can see one face of this loop acts as a north pole, other face acts as south pole. And see how to identify which face is a north pole and which face is south pole. So I'm taking south pole. Yes. And this is north pole. En. Okay. So here take now arrows for these two. Arrows for these two. You can see here this is now clockwise. If current appears to be clockwise, if current appears to be clockwise, then that phase is acting as south pole. Okay. And this is now, if a current appears to be anti-clockwise, that phase acts as north pole. Now in this diagram, current is anti-clockwise. So for us, it is anti-clockwise. So this phase acting as north pole, behind this phase acting as south pole. So a current carrying loop is acting as a magnetic dipole. Means it is acting as a magnet. It has two dipoles, north pole and south pole. If current appears to be clockwise, it is acting as south pole. If current appears to be anti-clockwise, that phase acts as north. So this is now magnetic dipole. And if you remember, while discussing electric dipole in electrostatics, we have defined electric dipole moment. In the same way, here also we define magnetic dipole moment. And if you remember in that, direction of electric dipole moment is from negative charge to positive charge, right? So here what we are doing is taking south pole as negative charge and we compare north pole with positive charge. That means direction of magnetic dipole moment is from south to north. I am repeating. We compare north pole with positive charge, south pole with negative charge. So electric dipole moment direction is negative to positive charge. Magnetic dipole moment direction is south pole to north pole. So in this direction, or in this diagram, this is anti-clockwise. So this face is now north pole. The face behind this one is south pole. So south to north. So direction of magnetic dipole moment is now outwards. Normal to plane of this board outwards. Or this can be taken as you just curl fingers of your right hand along the current flow. Thumb will be outwards. I am repeating. Curl fingers along the current flow of your right hand. Then thumb indicates direction of magnetic dipole moment. If you remember, the same logic we have taken while discussing circular motion, that is angular velocity direction, right? If particle is moving anti-clockwise, then direction of omega bar, it is outwards, normal to plane of circle, outwards. If it is clockwise, if you curl your fingers off your right hand, thumb is inwards. Exactly same logic here also. Okay, right. Let us now focus. What happens if you are placing a current carrying loop in a uniform magnetic field? I am taking here one rectangle. That means we are taking a wire. With the help of that wire, we are forming one rectangle. So we have taken one conducting wire. We are making one rectangle. Current is now I in this one. So I is now like this. It is a clockwise. So this phase is now clockwise means south pole. Behind is north pole. So magnetic field, sorry, magnetic dipole moment. It is into the board because south to north, right? Into the board. Let me take it as P, Q, R, S. Let us take field is now right side in the plane of the board, which is uniform. And let me take direction of B as positive X. Means we are taking this plane of the board as XY plane. This board is now in XY plane. Now focus carefully on the wire PQ. What is magnetic force? On PQ, there is no magnetic force because L bar, it is along B bar. That means between L bar and B bar, angle is 0. So on PQ, no magnetic force is acting. Okay. Next, coming to RS. Here angle is now 180. Again on this, no magnetic force is acting. Coming to SP. SP. See carefully SP. Direction of current is now along positive y-axis, means J cap. Field is now along positive x-axis, I cap. Now see here, L bar along positive y-axis, J cap. Okay. j cap, v bar along x-axis. It is I cap. So it is now L bar. It is j cap across, B is now direction is I cap. So it is now j cap. L bar direction is j cap, B bar is I cap. So j cap across I cap. I cap across j cap is a k cap. This is now minus k cap. That means the force acting on PS, it is into the board because we got this is now minus k cap because I cap across j cap is a k cap, j cap across I cap minus k cap. Minus k cap means it is into the board. It is into the board. Force acting on PS is into. Then on QR, it is outwards, right? On PS into the board, on QR outwards. That means on this torque will be, you can see torque will be, you can see if I'm taking this as axis, rotation will be now about this axis, right? Means if we see from the top, if we see from the top, it appears to be clockwise. I am repeating, just imagine you are watching this from the top. From the top means how it appears. Rotation is now clockwise, right? Rotation clockwise. Then see on PS and QR, forces of same magnitude but direction opposite. They form couple, right? So torque is given by force acting. See how much? Let me take this length. QR that is equal to L. RS it is equal to B. Then force acting it is I into length is B into B. This is modulus of force into separation between those two. Separation between those two. Wait. Force is length L, right? Not B. This is L. So ILB. Separation between those two forces is now B, right? Then see how much we get. L into, sorry, small b it is small b. It is a small b. Then see here, L into B, that gives area. This is now I into A into B. Okay. And here, if you observe, between magnetic dipole moment and field vector, angle is 90. Angle is 90. Okay. Suppose angle between M bar and B bar is not 90, it is a theta. Then this will be, then torque will be I into A into B into sine theta, where theta is angle between magnetic dipole moment vector and field vector. Or I can say angle between normal to the plane and field vector, because direction of dipole moment is normal to plane. So theta is angle between normal to the plane and field vector. Or it is the best one is between magnetic dipole moment vector and field vector. Okay. And one more thing, if we have n turns, it is like one turn, next one more turn. If you have n turns like this, n turns, turns, for one turn, this is IAB. For n turns, let us take here Kaplan for n turns. It becomes I into Kaplan. Okay. So this is now I into N into A, that is magnetic dipole moment into B into sine theta. So in vector form, this is taken as tau bar equal to m bar cross b bar. If you remember electric dipoles, there we have discussed like a torque. It is equal to m bar. Sorry, it is a p bar cross e bar. It is now m bar cross b bar. Okay. So torque is maximum if angle is 90. So in this, what is m bar? M bar. It is equal to I into N into A bar. M bar is known as magnetic. It is known as magnetic dipole moment, just like electric dipole moment. Okay. Next, corresponding to this potential energy, if you remember electric dipoles, there we have learned minus P bar cross E bar. Sorry, minus P bar dot E bar. It is now minus M bar dot B bar. So between these two angle is zero. Potential energy minimum. That is a stable equilibrium position. If angle between these two is now 180, potential energy is maximum. That is unstable equilibrium position. So whatever we have learned in electric dipoles, exactly same thing. M bar cross B bar. There we have learned P bar cross E bar. There we have learned P bar dot E bar. It is M bar dot B bar. And if you remember, there time period of small oscillations. Suppose this is now field vector. This is now magnetic dipole moment. This is M bar. And between these two angles is now theta. Suppose theta is very small, means initially m bar was along field vector, now slightly rotate, means through a small angle and leave it. Then magnetic dipole moment oscillates, or you can say it executes angular simple harmonic motion. Then time period of oscillations is given by 2 pi root I by mb. I'm taking directly from electric dipoles. Okay. In electric dipoles, we have taken in the place of M, it is P, electric dipole moment. In the place of B, it is E, electric field. So remaining as it is. So directly by comparing with electric dipole moment, electric dipoles, we can get all these conclusions. Okay. So this is a torque, potential energy, and time period of small oscillations, right?